Welcome, my name is Auke Hoekstra and I'm an expert on electric mobility at the Eindhoven University of Technology. It would seem that comparing the CO2 emissions of electric vehicles and fossil-fueled vehicles is straightforward. Unfortunately, a combination of complexity, novelty, European politics and lobbying has resulted in a lot of confusion. So much so that the CEO of Volkswagen, Herbert Diess, advises people to use my calculations, and the writers of the Tesla Impact Report say they have improved their calculations based on my work. I even have a large following on Twitter that calls me debunker-in-chief because I quickly correct bad calculations in the media. But after watching this lecture, you will be able to make good calculations yourself. And maybe you can even help to correct bad calculations that appear in the media. So let's start. On the screen, you see 3 documents I wrote that you will use as background information. You will also find the links in the supporting information, but if you pause the video, it's also easy to find them using Google. The structure I use when I teach people how to calculate it focuses on the six errors that many reports still make and how you can avoid them. Here we see the list of errors I introduce. Hey, wait. These are out of order. Oh, this is page 57 of the Tesla Impact Report 2021. Let's put them in the right order in which I introduced them. 6 errors to avoid when comparing CO2 emissions of electric vehicles. Let's start with the first one. Overestimating battery manufacturing. The biggest drawback of an electric vehicle is clearly that you have to produce a heavy, expensive and resource-intensive battery. I will talk more about battery production and recycling in a separate video, but for now it's important that we correctly calculate the greenhouse gas emissions of the battery production. Many studies rely on old battery production data, especially in scientific publications. This is often a problem because science is careful but slow. So you often see review studies of a few years old, using sources that are a few years older, and then these sources use practical measurements that are older still. So I advise to use company reports. Volkswagen and Tesla are examples of companies that report on manufacturing. Let's take the brand new Tesla 2021 Impact Report. This picture shows where the emissions come from the battery cell manufacturing. In the past, over 70% of emissions were caused by the last step, cell assembly. But as you can see from this picture, in modern gigafactories, most emissions now come from the stages before production. Just 23% of emissions in the battery cell occur in the actual factory. And most now occur during mining. This also means that it doesn't matter very much anymore where the battery factory is located. A lot of talk on that, but less important now. What matters is where the mine you buy the nickel, lithium or graphite is located and whether it uses, for example, solar cells in electric trucks. But this doesn't tell us what the emissions were. For that we have to look elsewhere. There's no specific battery data in the 2021 Impact Report either. But from the 2019 report, we know producing a Model 3 battery causes about 26 grams per mile. They calculate that the pack is used for 200,000 miles, which implies producing the pack emitted about 5,200 kilograms of CO2. If we then know the weighted average pack of a Tesla Model 3 contains about 70 kilowatt hours, we know the emissions per kilogram were 74 kilograms of CO2 per kilowatt hour. And right now, that's the rule of thumb I propose you use. Actually, I use 75 because that's a nicely round number. Looking at the new impact report, I noticed something was off though. First, I looked to the differences in production emissions and multiplying them by the number of kilometers, I got a production difference. And that was just 2.7 tons. That's too little. If that was just a battery, that would mean a production of about 38 kilograms of CO2 per kilowatt hour, which is less than is required for mining. That cannot be. Contacting Tesla, I found that they reduced emissions for the rest of the car, partly because the drivetrain is so much simpler. So in the future, I propose to look at the entire car and not only the battery, because it's apparently possible to improve the whole production due to simpler drivetrain. The second error, underestimating battery lifetime. Here you can be very short. Modern batteries outlast the car. So assumptions of replacing the battery halfway through the lifetime you still find sometimes are really, really wrong. The picture shows data my friend Professor Maarten Steinboeg publishes on his blog using the input of Marijn Kouwmans. And you see that in the beginning there were some problems with subpar battery management systems coupled with bad air cooling, but by now all companies look like this. They have good batteries, good battery management systems, and almost everyone uses good water cooling. So this is what you usually see. What I expect is actually that electric vehicles will be used much longer than internal combustion vehicles, because maintenance really doesn't become more expensive when the car gets older, since the motor lasts practically forever without maintenance. Okay, next error, assuming an unchanged electricity mix over the lifetime of the vehicle. This one is really important because most people still do it wrong, mostly because they are, well, I think, to be quite honest, lazy or insecure. Tesla also doesn't do this in their impact report, by the way, because they want to be conservative. We do life cycle analysis here. Life cycle analysis means adding all emissions from cradle to grave. And since the electricity grid becomes greener over time, the emissions of the electric vehicle will become lower as it drives to its grave. Many people ignore this, which negatively affects the EV calculations, and it's simply wrong. I understand some value from the past is easier to obtain, seems like a safe bet, but science is not about being safe. Science is about being right. Look at the picture. It shows the CO2 emissions per kilowatt hour of electricity in Europe over time. Most reports would still take a value of 300 grams per kilowatt hour because it's easy to find. But the average mix of the electric vehicle over its lifetime will be closer to 125 grams or so. Recent research leads me to believe that you have to add something to that. About 25% to this you have to add because of coal mining and gas production, especially the fugitive emissions of both. So then it becomes 156 grams per kilowatt hour. So you always must take the average over the lifetime of the vehicle in the area where you want to make the comparison. If you want to be really precise, you can incorporate how much the vehicle might drive in different years. And to be quite honest, in the first years it drives more. See the document comparing lifetime greenhouse gas emissions, mentioned in the beginning, for more details. Then, the error of using unrealistic tests for energy use. This one really bugs me, because especially in Europe, we are messing up the science. We are knowingly lying to consumers, all about the energy use of cars and to make it lower. Look at 2016 in the picture. While car makers and politicians were congratulating each other on how the EU was reducing emissions, these improvements only existed in the laboratory. In reality, the cars emitted 40% more than on paper. And everybody who cared to look knew. Only with Dieselgate were politicians and car makers forced to face the music. With the new WLTP tests, they are still paid for by the manufacturers, and undoubtedly they are already 40% better than reality right now, and they will get less realistic over time. It's especially bad for plug-in hybrids. Here the real emissions are already 2 to 4 times higher than the official WLTP measurements. I predict this will become something of a new Dieselgate. So don't use WLTP. Use tests that are non-political. I encourage everybody to use spritmonitor.de or the American EPA. At least there nobody is paid to falsify the results. If we use spritmonitor.de, we get 0.19 kilowatt hour per kilometer for the Tesla Model 3. For the Volkswagen Golf, which is arguably a less luxurious and smaller car, we get 7.22 liters per kilometer. No, enough said. Then the fifth error of excluding fuel production emissions. Just like electricity has to be produced, fuel has to be produced. And on average, this adds 25 to 30% to the emissions of internal combustion engines. The picture shows that the place where it's produced matters a lot. My advice right now is to take 3,310 grams for diesel and 3,140 grams per liter for gasoline. But find your own values. If they are close to this, you're probably doing it right. So as you can see, the values in the folder are wrong on 2 counts. First, because the official tests are much more optimistic than reality, especially in Europe. Second, because the number in the folder assumes that gasoline and diesel appear as nothing. So we often hear the claim that it's nonsense to say EVs don't emit CO2, and it's usually the start of some diatribe. But combustion vehicles emit a lot more than is admitted to. Let's bring it together. Let's make the complete calculation. We know the Model 3 emits 50 grams per kilometer for the production. For the comparable internal combustion engine, it was 39 grams. We know that Tesla uses 0.19 kilowatt hours per kilometer. And 1 kilowatt hour emits 156 grams. So if we multiply, we get 30 grams per kilometer. And now we get a big difference. For the combustion engine, the same method gives us 227 grams per kilometer. If we add all together, we get 80 grams for the Model 3 and 266 grams for the combustion vehicle. That means electric vehicles already emit around 30% of what the comparable ICE vehicle emits, and in the future will only get less. Then finally, I want to ask people to think about the whole system. Because compared to the whole system, all the previous stuff was just small potatoes. The really big difference between combustion engines and electric engines is that combustion engines are at the end of the road. They cannot remove CO2 emissions much more. Now imagine a future with solar panels and windmills, producing the energy needed to produce solar panels and windmills. You get very close to zero emission for your energy then. Imagine those same solar panels and windmills producing the energy needed in the mines and the factories while driving your electric vehicle. Electric vehicles could emit close to nothing in such a scenario. And now imagine, system thinking, we go even further than the electric vehicle. I'm from the Netherlands, so I'm a fan of bikes and public transit, but we also love comfort and personal transportation, of course. I firmly believe self-driving will make every vehicle, also smaller vehicles, a taxi in the future. We simulated that, what that could mean in terms of vehicle size and impact, and we found the following. 10 times less vehicles smaller on average. 15 times less material and particle emissions. 100 times less parking space in the city, and children can play safely. And all that from simply switching from privately owned cars to shared autonomous electric vehicles. So electric vehicles already emit less than 1/3 of combustion vehicles, right? The difference between the two will only get larger. But if we really want to think out of the box, we must think beyond the electric cars. And that's it. Thank you very much.